Hi everyone, we're really happy to have Shraga here today. We're working on data science and AI, and he's finished a PhD in Technion, and he's now a postdoc in Eastern University. So,
Thank you, Omar, for the introduction. So my name is Roee. I'm currently a postdoc at Northeastern University, and today I'm going to tell you about my research. Before we dive in, as you all know, data is everywhere. We have a lot of data, and there is a lot of interesting questions that we can ask about the data. Some of them are, where do we store all of this data? How do we manage all of this data? And what is kind of like my go-to question would be, what can we do with all of this data? And what follows, there is a nice concept that was developed during the last year, which is called the data lake, which is a general name for a centralized repository that not only stores data, but also processes data. So kind of like the difference between what used to be a data storage or a warehouse of data is that data lakes should also make sense out of the data that we have. And when we talk about data, or data lake in general, we talk about open data, which is the main source of such data lake. And open data, again, is a kind of a new concept that is quite catched on during the last years that talk about open data. Obviously, and a lot of you may raise questions about privacy of data, but for now, let's assume that we have open data that people can use. And it's kind of common nowadays. And this open data is the main source of these concepts, as I referred to before, which are data lakes. And again, the main idea would be that such data lake not only stores data and thinks about the prospects of how and where do we store the data, but also how to make sense in terms of discovering data, linkage of data, matching data, and so on. Data, we come to data science, which is my main incentive. And when we talk about data science, we talk about the 80-20 rules, 80-20 rule. And for those of you who don't know the 80-20 rule of data science, this means that 80% of time that data scientists spend working with data is basically on finding, cleaning, and organizing data, while only 20% are spent on actually performing the analysis. And all these concepts are, as I see, data management research, which is my main research topic. It's not only how to manage data and store data, but also how to find, clean, and organize data. There are also some alternative takes on the 80-20 rule. Here, for example, Big Data Borat, which is a nice Twitter user, talks about 80% of time is spent on preparing the data and 20% of time is spent on complaining, how do I need to prepare the data? So for those of you who work with data, can definitely relate to this alternative take. My research follows four main aspects of data science, namely managing data versions, discovering valuable data, integrating different pieces of data, and improving data quality. And plugging it all together, one of the main objectives that I have in my research would be to take this 80-20% rule that I mentioned before, and maybe improving it into a 60-40%. Right. So I'm not aiming towards fully automated data preparation, fully automated data discovery, data science, and so on. I'm trying to improve it a little bit, trying to make better data for better science. So before I dive in on two of my recent works, I want to give you a brief overview of my research, kind of like the main objectives of what I do in my research. Before that, and I mentioned that before multiple times in my meetings today, one of the main problems that we have with data nowadays is that it lacks semantics. When I say lacks semantics, this means that we don't have a lot of sources to understand the meaning of data. And this is usually characterized by unreliable metadata, or sometimes not existing metadata, missing data, inconsistent values, and so on, which makes all of these problems are very challenging and very hard to handle. To illustrate my research, I want to introduce to you a group of data scientists that work with some data source that they have. Here, for example, is a tabular data that talks about patient information, and they have some question in mind. Their question here in our illustrative example would be, I want to predict whether a patient has Crohn's disease or not, right? And there are other interesting questions that I can ask, but let's, for the sake of the example, assume that this is the main question that we want to ask. Now, this data piece may be not sufficient to answer these kind of questions. And in what follows, our work tries to develop some foundations on discovering additional data pieces that can help these data scientists, or in general, people that work with data, in terms of finding more valuable data. And the information retrieval perspective of such research or of such task would be to use some keyword search. For example, I can ask a query such as Crohn's patient data over such a data lake, a table repository, and so on. So such source of data sets, data sources, tables, and so on, and find a table that looks to be relevant to the question that I asked. However, it's not trivial how it's relevant to the data that I'm looking at. And specifically on this task, again, the information retrieval perspective of data discovery, we had a nice work that I presented at SIG-IR 2020 that developed a multimodal deep learning approach to such a problem. So given a keyword search and a repository of table, retrieving a set of relevant tables to this keyword search. However, it's not trivial how one can use this table when they have this data at hand. And what follows, the data management perspective highlights the table as a query. So instead of plugging in some keyword search that tries to find relevant data, we can directly search the table itself as our query, and then start asking questions, for example, from a machine learning point of view. One question might be, I have this data source, but I don't have enough features. What I need more features in my data, for example, to predict Crohn's better. And this kind of questions go back to traditional questions in data management. And here, for example, we can talk about finding joinable tables. Or in other words, I want to find a table that is not only relevant to what I'm trying to find or what I'm trying to achieve, but also makes sense out of the way that I can use this data. For example, if I found a joinable table here, I can easily, or not that easily as I will explain later, add it to my data, and it is actually relevant to what I'm trying to achieve. Another interesting question that we can ask here would be, I need more data points, right? So again, as a machine learning practitioner or as a data scientist in general, I can say, I don't have enough data to generalize, or I don't have enough data to claim for statistical significance. So at one end, I can say, oh, maybe I can augment data. However, if I have some existing source of tables that may contain some irrelevant information, I can also search, again, from a data management point of view, I can also search for unionable tables. Or in other words, tables that I can union into my data and generate new data points in my data. In a paper that we're going to present next year in SIGMOD, we presented a data-driven approach to this problem, or in other words, facing these issues that I mentioned before, having unreliable metadata, a lot of missing data, and so on. We aim to find an algorithm that only looks at the data itself within the tables that we look at to find these unionable tables. Any questions so far? Great, thanks.
So
sure.
why not have all the data that you have on Ed Glover or whatever person there be sort of the representation and then learn using maybe too much attributes?
This is a great question. And first of all, this is part of the things that we do. So one objective that we have, one alternative for finding immutable tables is to find a representation for different tuples and search for these tuples in different repositories of data. So this is one thing. The second question would be how to integrate these different sources. So one cannot assume that we have all the information that we need as additional attributes or additional things. And one thing that we try to do is to find the right way to integrate different pieces of data. And this is what I will show later on in this presentation. Yes.
This is how do you know that Sam Hill has rows? How do you know that Y usually the Y is rows?
Again, sorry.
How do you know that Sam Hill has rows?
Oh, great question. So as I mentioned, we look at data-driven approach. Here specifically, it's a toy example. So the 1 and 0s can actually relate to any other label data. But specifically what we do is we look at the semantics of the column itself, the values that we have in the column. And this work specifically, we build on top of knowledge graphs. So we map the values into some mediator knowledge graph and try to understand whether two columns refer to the same value in a knowledge graph. In an additional work, again, which is in progress, we look at contrastive learning to represent columns in an embedding and use it to find the same semantics between different columns. Yeah.
When you evaluate this kind of stuff, where do you get the ground truth? Like, how do you know that you found all the union level or the correct union level?
Great question. So this is a major issue. We specifically came into this problem where benchmarks were created already. So we had benchmarks. However, this is not a trivial thing to do. One thing that people do nowadays is basically assume that they don't have headers at all. And what they do, they split the data in different ways. So for example, if I want to find unitable tables, I can basically randomly select different pieces of data and separate them into different tables. And then I know these are unitable because they came from the same source, but our algorithm doesn't know that. So we have some techniques to do that. A lot of manual labeling, which I have a lot of criticism of. I will refer to that really briefly later on in my presentation, but a combination between techniques that we know that generate joinable and unitable tables and some human labeled data. Great, thank you for this. Great, so we discovered our relevant data. We have different pieces of data, but then it's not trivial how to integrate these pieces of data. And here specifically, and I think this refers to, again, it looks easy, but in practice, it's quite hard, how to vertically integrate different tables. So assume, for example, that we have these two tables. It's not trivial that name and full refer to the same thing, weight and kilograms refer to the same thing, and so on, especially if I don't have the headers. So here, for example, some embedding model, some transformer over the names of the column may help me here. However, this is not a trivial task, and this is something that I worked on mainly during my PhD, where we developed algorithms that try to make sense out of the correspondences between different attributes of data. And specifically in a paper that I presented in VLB 2020, we had a novel use of deep learning to this problem, facing different challenges of lack of data, labeled data, and other issues that we handled. Happy to elaborate more offline if someone is interested. A second question that someone can ask in terms of integrating the data is what should be horizontally integrated? So we have different tuples. Some of them refer to the same thing. For example, Laura page here and Laura M page. How do we find these correspondences in an automated way? Specifically in another paper that we're going to present in Sigma 23, we have a graph neural network solution to this problem that builds on top of a transformer, a language model that aims to find these matching tuples between different data sets. And this is what we do. And another question, which refers to a question that was asked before, is another perspective of my PhD research, which is who should do this integration, right? So people talk about fully automated solutions, but we need some labeled data. Even if we want to apply supervised learning, and let's assume for now that we aim to apply supervised learning, we need some labeled data. And in what follows in some of my works in my PhD, I tried to look at people that label our data. And specifically, I don't expect you to look in specific details into this graph, but in general, what it shows is that the much time people spend on making a decision, so it can be a matching decision to label our matching data, it can be other labeling other labeling tasks that we considered in other works, they become less accurate and less confident in the label or in the decision that they provide for us. And this is a nice area to explore because using these insights, this one and other insights, we can actually identify matching experts. So experts that can, or matching human experts that can actually label my data. We can calibrate matching decisions if we have some human in the loop. And we can also go and improve label quality if I have some new data set that I'm trying to label. Again, happy to elaborate more offline if someone has some more specific questions there.
Can you
Yes.
go back to the previous slide?
Yes.
Can you elaborate just for 1 minute, maybe about, no, previous.
Oh, yeah.
Previous, yeah, the horizontal.
Yes, of course. This
So,
one.
yeah, so what exactly, like, the challenges here?
Oh, the challenges is again the theme here, lack of semantics. So here, just to illustrate the problem, I plugged in some very easy, some solvable, very easy things to do. For example, we have Laura Page here and Laura Aim.
Yeah, so is this really a language thing, like an NLP thing? What type of,
Great
I mean,
question.
is this a database question?
Yes.
or-
So this specific question, which is usually referred to as entity resolution, entity matching, sometimes record linkage, has research in a lot of neighboring communities, specifically NLPs and databases are kind of like the main hubs for these kind of questions. And it depends on the data. One thing that strikes me as a challenge nowadays is working on these numeric data. Because when you look at the state-of-the-art solutions, they mainly look at this as a language kind of thing, right? So I have sentence, we can adopt it somehow, we can add on some interesting takes on how this data is structured. Again, I can elaborate more on how we look at it offline. But again, the main challenge would be the numbers and so on. But I agree with you. Some of the main state-of-the-art techniques nowadays look at adapting language model, assuming that the main source of data that exists in table or is of interest is in natural language. Thanks. Great. Okay, and one final question in terms of integration, and I will elaborate more on this later on in my in my presentation, is given that we have our tables that we want to integrate, and we already know what should be integrated, how we actually do the integration in practice. So what is the efficient algorithm, the correct algorithm that takes these free tables and bring it into one integrated table that I can, as a data scientist, work with. And as I mentioned, I'm going to elaborate more on that in my talk today. And specifically, I'm going to introduce to you a new algorithm that we created. And I'm going to show you, not in details, but briefly, that it is correct and efficient. And this is a work we're going to present next year in VLDB. Another perspective of my research in terms of data is working with the data. So let's assume that we discovered all the data that we need, we integrated what we needed to integrate. Now we need to work with the data. And one interesting aspect of that nowadays would be collaborative data science. So what happens if different users work with the same data or with collaborate on data sets that they're going to share insights or information of? And specifically, I refer to this problem as data versioning. So we have different versions of the same data. So as you can see here, this table was generated using this table. However, we have some additions to the table. And here, for simplicity, let's assume that we have only added columns. And what we try to do is to explain these changes. And again, if time permits, I'm going to briefly show you our solution of how to reverse engineer the functions that were used to generate these columns. And one question that you can ask me, why is this a problem, right? So if we look at IDC, which is the International Data Corporation, they talk about 90% of new generated data is actually replicated. So in other words, 90% of the data that is generated nowadays is actually versions of each other. And what we aim to do here in this research in general is to try to make sense of the different versions of the same data that exist out there. In addition, I have some other works about working with data. For example, how to generate high quality data to begin with, how to understand the underlying concept of data, for example, using research on process mining, and how to overcome low quality or missing data and perform some tasks that we can perform, knowing that we have some inconsistencies or some missing or low quality. So this is the overview of my research in a nutshell. It was supposed to be quicker, but via Zoom and so on. So it will get to its point, looking into data versioning, data discovery, data integration, and data quality. And now I want to focus on two of my recent works. The first looks at how to integrate data lake tables, so how to integrate tables nowadays with the challenges that we have with current day data. And the second one talks about explaining dataset changes. Any questions so far? Great, thank you. Great. So now we're going to talk about data integration in practice, or what we had before. So we had 3 tables. Now I added names for consistency and for us to be able to use them. And what we need to do, we want to integrate these 3 tables into one table that has all the information or all the facts that these 3 tables had before. So for those of you who know some of the operators that exist, may tell me, okay, so just join the table, right? So you have an operator to do just that, or specifically here, because we want to maintain tuples that do not have a corresponding tuple in the other table, you can tell me, okay, auto join the table. A quick example of what an auto join looks like. If I have these 2 tables, so we have one tuple that has a corresponding tuple here, one here that doesn't have a corresponding tuple here, and one here that doesn't have a corresponding tuple here. The auto join would look like this. So we have this join tuple here, and we have the Sam Hill here padded with nulls, and the Edl over here padded with nulls. Okay, so you can say, okay, just join the tables. However, this is not that easy to do, because at the beginning, it looks nice and easy when we integrated T1, T2, and then T3. However, if we first integrate T2, then T3, and then T1, we get a different result. Moreover, this result is not correct by definition, right? So if you look here, you see a pair of tuples that should have been integrated or seem like they shouldn't have been integrated. And I'm going to tell you that they should have been integrated. And the main reason for that is that the outer join operator is not associative. Right? Yeah, go ahead.
If people had ideas like we all had,
Yeah.
would this problem go away?
If people had ideas.
Ideas.
Oh, yeah.
Identification.
Yeah, definitely.
Number.
In a sense, yes.
You usually do have, like we all do
Yeah.
have.
So first of all, the first answer is no, because here I didn't hide any data. So at the example that I have here, at the example that I have here, I didn't even have null values. I have complete information. So I have name here, I have name here, name here. So everything is complete and clean as you refer to. What I'm gonna show you now that even if everything is clean, you don't have an efficient algorithm to do that to date. And if you introduce some noise into it, for example, even one null value, you still won't get the result that you're trying to get. So in a sense, you have some research on what happens when you have full data. You have much less research when you have incomplete data, and this is what we try to zoom at. And building on top of that, and I'm sorry for jumping here. Building on top of that, let's go back to our 3 tables and replace just one value by that value. Right? So we have the 3 exact tables as we referred to before, but now I introduce this one null value, right? And I use null here, this symbol here as a null. Now let's assume that you told me that I need to integrate T1, T2, and then T3. So someone gave me the correct order. However, because I have this null value, now I still don't get the result there. Right? So even if I had, before I had the clean information and I had the issue with the associativity, or specifically I needed to, in a sense, and this is what happens in literature when people assume that they don't have a lot of tables, they just check all the orders, and this obviously becomes computationally hard. But here, just introducing just one null value creates, again, something that looks inconsistent. And And in what follows, people came up with some general semantics or with an operator that can be considered as an associative alternative of outer join that is called full disjunction. Right? And the full disjunction was shown to maximally integrate the different tuples in different tables by Ullman and others. And the idea would be that it is very hard to implement, and this is what we aim to do here efficiently. However, it returns the result that we want to see, right? So we can actually prove that it is correct. And going to our algorithm, we have a full pipeline of going from input tables, so general input tables that can have missing data and so on, to an integrated table. And what I'm going to share more right now, because this is what I talked about now, would be our new full disjunction. Okay.
So,
Yeah.
can't you just
Sure.
go over the table, like one slide back, go
Yeah.
over the table and just index on the unique ID and then with a hash or something, and then that will join everything?
Good question. So first of all, the issue with that, and this is what people did, is that you don't know the order of the join that generates the correct result, right? So as I mentioned before, if you would integrate T1, T2, and T3, even now that we have a null value, you won't get the same result as you would expect, right? So the correct result, you know. So in terms of efficiency, this is what people do to make the algorithm itself efficient. However, the semantics of the algorithm or the implementation still requires you to check all the orders of the algorithm. And trying to deal with that, people came up with different solutions that had issues, and this is the slide that I stopped. And but again, the retrieval part in these kind of works is not a big issue, because we can assume that we have the same name. So this is not an issue in that sense. The issue would be to find the right order that creates the correct tuples, or in the words that literature uses, maximally integrated tuples. Okay. Yeah.
What is the correct thing with respect to C? Is there a definition or?
Yes, there is a formal definition of that uses a definition that I'm going to show you now that talks about subsumable tuples. Kind of intuitively, you can think about this case where you don't have any tuple that is subsumed in another tuple. This is kind of like the definition. And also you need to have all the information from the different tables. So this is what is considered as a maximally integrated tuple. And specifically, we use this subsumption here. So I'm going to show you how it looks like.
It's not correct that whatever order of joins you apply, you can post-process the result and arrive at that result.
It is an option, but it's not scalable, right? So in a sense, what you could have done, and this is here, consider all join orders or even some, finding spanning trees of different orders or different join paths. But this is an issue of scale. So the main issue with that would be scale not correctly. So for example, there are some other alternative that looks at a tuple based, and then you cannot show correctness because it looks at each tuple by itself. But happy to talk more.
Maybe Tomo's question is why not pick one arbitrary join order and then fix the table that's in the spot?
In a sense, this is exactly what we do. So instead of doing that with join that over integrates different things, now I'm going to show you an outer union, which instead of the outer join that already integrates things that we wouldn't expect it to integrate, outer union does not do that. And what we do is we fix the result. So this is exactly, your intuition is correct because this is exactly what we do. Yes.
What happens if you want to allow small errors? Like you have two entries that are completely identical, but in one my height is 175 and in one it's 174. It's probably still the same entry.
Yeah, I'm smiling because this is something that we didn't do in this work specifically. It's basically considering fuzzy joins, right? So fuzzy join would be a case where you have two very similar names, as I showed before, or very similar heights, and you still join them. And this works specifically since it's kind of like preliminary in this new space. We mainly focused on what happens when we have missing data, and what happens when we don't have foreign key, primary key constraints. So when we don't have the
Because
same name,
it's,
but I agree with you.
in the context of your algorithm, it seems to introduce interesting questions, I think.
Yes, exactly. I completely agree. And one kind of natural extension of that would be to look at, again, in the literature of the database literature, it's called fuzzy joins, but again, kind of like not exact matches. I completely agree. As I mentioned before, in other words, we looked at that, right? So when I mentioned unionable tables, this is exactly what we did, right? So, and also the entity resolution work. However, in this work, for the moment, we decided to focus on exact matches, but this is a clear and interesting extension. So to illustrate or to introduce my algorithm, I need to give you a quick crash course in some of the less known operators of data management. So try to bear with me because we use them in our algorithm. And the first one refers to the question that I had before, is outer union. So I mentioned outer join, I mentioned union, and basically you can intuitively think about that as a union that also pads the value with null. So instead of the outer join that force this integration between these two tuples, we leave it as is. In other words, we union the tuples. So if we have unionable tuples, and in this case, we didn't have anything because we don't have any tuple that has the same schema, the same attributes as in the two tables, we basically pad the value with null values, allowing our algorithm to decide later on what should be combined together and what shouldn't, right? And this becomes a space issue at the beginning because we can generate a lot of duplicates here. However, since we have other efficient algorithms to solve these things, then it becomes a very natural thing. Okay. But again, as I mentioned, when we do outer union, then we have a lot of duplicates or a lot of things that seem to be integrated. And for that, I want to illustrate to you two additional operators. One of them is subsumable tuples or subsumptions, as I mentioned before, and the second one would be complementation, which is somewhat similar. Subsumption, and bear with me, I'm not going to go into the formal definition, but we have one. Happy to elaborate more offline. Two subsumable tuples look like that. So they have the same non-null values. So if you look at these two tuples here, they have the same non-null values. So wherever they have a non-null value, the two corresponding attributes, so here, lower page, 75, 75, they have the same values. The one that we can call a subsuming tuple would have a non-null value where the other one has a null. So again, you can think of an alternative way to solve these issues here, because what we do in our algorithm would be to combine them together, right? Because we have one subsumable tuple here. The second operator that I want to introduce to you is called complementation, and in a sense, it can be thought of very similar to subsumption. And what I like to call, if in subsumption, one tuple brings to the table everything that we need, in complementation, we look at a scenario where two of the tuples bring something to the picture. And again, we have, as before, we have the same non-null values in corresponding attributes. However, in complementing tuples, the first tuple or one tuple has non-null values where the other one has a null value, and the second one also has some non-null value where the first one has. Right, so these operators look kind of intuitive, kind of straightforward, but they have very efficient implementations in practice that we can use as a part of our algorithm. So our algorithm basically applies these three operators as a sequence. So first we outer union the different tables that we have as input. Then we solve the complementation. So we find these complementing tuples and combine them together, and then apply subsumption. Using complementation was introduced in the literature before. However, one of the main assumptions, and I referred to that before, was that the input doesn't have a null value. And I'm going to show you why our kind of key idea in this algorithm, which is kind of a simplistic one in generating labeled nulls, solves this issue. So this issue is as follows. Let's assume that we have two tables here, Alice 21, Bob 38, and we have another table that we want to outer union here. Alice, we don't have the age, and Y is 1, and someone that we don't know their name, 38 and 0. We apply this outer union as I mentioned before, and we get this input. And then if we apply complementation, we get this output. So we say that Alice is 21 with a label of 1, and Bob with 38 with a label of 0. If you take a closer look, this is not what the input told us, right? Are all Alice's 21 years old? I guess not. Are all 38 years old named Bob? And the main reason for that is that the complementation algorithm or the complementation operator that I mentioned before cannot distinguish between different nulls, right? So for the algorithm, these null values are the same. They don't distinguish between them. And in what follows, it creates some inconsistent values that can be harmful for the output that we are trying to. And what we do here, again, it's kind of a simple trick that solves it. And what we do here is we replace these null values by a label nulls or unique label nulls. Now, our algorithm thinks that these null values are unique values, right? So the algorithm itself, the operator itself, and the efficient implementation of it doesn't know that these null values are actually null values, but we know that. So in what follows, we can use an efficient implementation algorithm or efficient implementation of the complement operator and get the same result or the correct result that we can actually prove at the end. And specifically, we show that our algorithm actually computes the correct full disjunction as it was defined in the literature. The proof is in the paper, and for the sake of time, I'm not going to go into a lot of details here, but happy to elaborate more offline. We also show that it provides the best theoretical guarantee to date, computing the full disjunction. And specifically here, we use input-output complexity, which is very common in the data management community following Yanakakis. And specifically, we show that this is better than the best theoretical guarantee to date in the literature. But in addition to these theoretical guarantees, what we wanted to show is that it always also works, and it also works very good in practice. While our theoretical guarantee was a smidge better than what existed in the literature, our algorithm, because we have some efficient algorithm that also goes back to some efficient indexing techniques of the values that we have there, actually performs 10 times as fast as the existing baseline, which is very nice. And we actually showed that on 4 different data lake benchmarks that included, for example, integration sets, so these tables that needs to be integrated, that has more than 50 tables, right? So the issue of, or the alternative of trying different orders of join when you have 50 tables doesn't seem like something that is efficient or actually feasible to do. Code, benchmarks, and everything are online, so if anyone wants, happy to elaborate more offline and answer any question. With the time that I have left, I want to introduce you more of an engineering algorithm or more of a new problem that we look at, which is semantic data versioning. And then I'm going to aim at finishing that at the people that needs to leave at 2 can leave. And then I'm going to elaborate more on my future direction and happy to take any additional questions or so. So I mentioned that before in my introduction that we have a scenario of collaborative data science. And for the sake of the example, let's assume that we have some user A that created this version of the data, and user A collaborates with user B and generated these new features as a part of their feature engineering or general data science. And as it seems, or also supported in the literature, people do not have proper documentation of what they do with data. Right? It became kind of a common practice to document code. However, with data, it's not something that people do in a common way. And this is what we are trying to find. So we are trying to explain these changes. In our algorithm, which we termed explain the V, we have 4 different stages. And I'm going to focus and give you a brief example of one of these stages. The stages are finding the origin, or in other words, finding these attributes that were used in generating these new tuple that I'm trying, or these new attributes that I'm trying to explain here. Here, for example, and this goes back to data management problems such as finding functional dependencies or discovering functional dependencies. Generating different explanations, and I'll give you a brief example of one method that we do, which is quite simplistic and you all know it. Then we started asking questions of how we evaluate these kind of explanations, right? We have a user that actually needs to use this, or we have a scenario where we try to evaluate or understand whether this solution is beneficial or explanation is beneficial. So how we actually evaluate that. So we have the 3 different measures. I'm going to show you briefly what they need. And finally, we need to select one for the user, for the output user, to kind of like add some additional semantics. For example, if we had this new column here that was created, we found this function, then a user can say, oh, what the user tried to do here is to add a BMI. Explanations exist everywhere. In the data, in the AI community, we're trying to explain model decisions using features, using rules, using data, and so on. In the data management community, we're trying to explain query answer using provenance, for example, provenance. And we're also trying to explain some data generation using data transformation. And this is what we do in this work. And specifically for our work, mainly covered textual transformations. So they're trying to explain some textual transformation, some of the things that you can consider. Someone split a full name into first name and last. What we try to complete here, what we try to fill the gap here would be some other kind of like underexplored types, for example, numeric data or categorical data. For the sake of time, I'm going to skip this numeric explanations. But briefly, I can tell you that what we do here is we position that as a regression problem, trying to find these numeric explanations. But for the sake of time, I want to introduce to you the categorical explanation, which again is casted as a machine learning problem. And specifically, kind of a well-known machine learning problem, which is classification. So let's assume that someone told us that A5, and this is a part of our algorithm, was generated using age. What we can do here is we can fit a decision tree that tells us that the values that were generated in A5 follow this pattern, right? So if age is over 50, then assign a value of 1, and if the age is under 50, then assign a value of 2. Then some of the interesting questions that we need to ask here, look at this transformation. So when we look at machine learning, what they're trying to achieve is, can we predict A5 nicely? Right? Can we predict A5 using age in a correct manner? So we want to do that as well, right? So we want to reverse engineer the values. And for that, we introduce the validity measure. For example, we want to say that the measure is valid if the values itself using these transformations are restored correctly. Right? If I had, for example, this tree here saying that rooted at age over 45, then the values would not be restored correctly, because the value here of the first tuple would be 1 instead of 2. So we look at perspectives of validity.
So you're aiming at 0 training error?
Yes, exactly. Because we're trying to find here in validity, yes, we're trying to.
If there is no 0 training error, is assuming a lot.
Again, sorry?
0 training error is assuming a lot.
Yes, I agree. I agree with you.
Okay.
So there, we have some transformations that we cannot explain. For example, these transformations that people just added, right? So I can just add something without doing the transformation. And we had some other issues. If we actually look at literature, they aim at a maximum validity. So they look at validity as a binary question, exactly as you asked. And we had some criticism over that. So we instead look at validity as a confidence point of view, right? So we can claim that this one is not, we can say that this one is not valid, but it is valid with the 75% confidence. So this is exactly some of the criticism that we had when we designed this and looked at different approaches. Other measures that we created would be generalizability. So for example, let's assume that this is not the only instance that exists in the world. Then we ask ourselves, can this one be applied also if we had some other instances? And for that, let's assume for now that the original intent was people over 50, then this tree is valid because if the age is over 80, is over 65, it still maintains the same values in the instance that we saw here. However, if we had another value here with the age of 55, then the value would not be restored, correct? And this is what we claim as generalizability. And finally, we also looked at some quantitative measures of explainability. This is kind of something that we try to go to would be some quantitative measures of explainability. Here, for example, we can look at the size of the model, right? So we can estimate the size of the model and claim that a model that is more compact and it has some, there are some interesting works on explainable AI that looks at that if the model is smaller, then it's easier for people to understand, right? Some of the takeaways and lessons learned, again, for the, yeah,
So-
go ahead.
How is your decision tree algorithm differs from sort of classical machine learning decisions? The algorithm like CART, C4.5?
The answer, it's not different.
Okay.
We use the same ones. Some of the things that we do, we want to apply more than one decision tree and understand in terms of evaluation, which is something that people.
So it's a decision forest.
Yeah, in a sense, not exactly. Yes,
Okay.
yes, sure. Some of the interesting takeaways, and this refers to the questions here. So we do not claim at novelty in terms of developing new machine learning algorithms here, but we do claim at exploring some of the unexplored data types and data lakes. People do not look at numeric data and data lakes for some reason, and we found that some of simple existing techniques in ML can be very beneficial to make some sense out of numeric data. Documented data science is very important. We can reverse engineer some of it using our techniques. And finally, explainability is hard to explain. So one thing that we did here is to develop some quantitative measures of explainability, even if it's before we apply some user study. I think it's very important to develop some quantitative explainability measures. Yeah, so I think it's now 2, and I was told that I can go a bit over, but this is the main thing, and I'm happy to elaborate more on future directions and take some more questions, but feel free to leave now or leave it on to. Thank you. Thank you so much. Okay, so some of my future directions. So the first future direction actually follows the main things that I did so far in terms of data discovery, integration mainly, and aims to ask some interesting questions in terms of, can we introduce some additional requirements when we do this search or when we do this discovery? For example, can we not only find tables that can help us better predict Crohn's disease, but also preserve some distribution and representation? For example, we want to have the same amount of females and males. We want to have an equal distribution of different. We want to have a group representation, so we have some racial representation in our data, and so on. Can we exclude, to begin with, within the discovery phase, can we exclude some sensitive attributes or features as they are referred to in the literature that that shouldn't be used when we do these tasks? And these all go into what is now referred to as responsible data integration. So similar to the advancement in the responsible AI, these issues are very important also when we talk about data discovery and data integration. Another interesting direction that again follows through with the things that I do is to develop some more foundations to data discovery. So data discovery was developed mainly in the data in the data management community. And what follows, the main objectives and the main things that people look at would be effective indexes, how to create effective indexes, how do we store of this data. And when we talk about current day's work, when people look at the semantics of such processes, I think we need some more foundations to it. For example, when we look at information retrieval, there are a lot of foundations in probabilistic models and other interesting foundations that we can also develop in data discovery. For example, what does it mean to be a good table? What does it mean to be a relevant table? Can we define some underlying concept with these kind of problems and use them when we do these tests? And finally, some of my kind of like things that I want to think of and still not there would be multimodal data discovery. So we have a lot of different modalities of data out there, some of which are highly explored by the people that sit in this room, from vision data, from textual data, and so on. And some of the interesting questions that people can ask nowadays is that, let's assume that I have this tabular data already. Can I use some other modalities to improve or to extend my data, knowing that what I want to use is tabular data, what I want to stick with as tabular data. And finally, and I referred to that quite briefly before, also willing to continue my journey into understanding human behavior for data science, or in terms of human in the loop, or what I like to call as people view now, explainable AI is very, very important, but I think it's very important to also explore how we explain humans to AI. So I gave an example before how to interpret or we use labels that are generated by humans, but there are a lot of other interesting aspects of people that are included in the data science field, but we need to do better in terms of unfolding. So this is another interesting direction that I have. Yeah, so a lot of thank yous, a lot of nice people and highly qualified people contributing to my research. So it's a great opportunity to say thank you to all of these people. And thank you guys for listening and sitting over at 2 p.m. and listening to me talk. So I'm happy to take some more questions, and I'm here around if anyone wants to talk more offline or thank you.
Thank you very much for the presentation. So I have sort of a very practical question. Do you know if like there are any plans to develop like Python libraries that we do with techniques, let's say, build up metas or as a practitioner?
Yeah, it's a great question. So working in the States, my assumption would be that my PI would take that into a product sooner or later, especially the work that I choose. For the moment, we basically develop prototypes, are publicly available and people can use them, but I won't call them something that practitioners can use. If you would ask me what people do nowadays, they just assume one order of auto join and use pandas to do the start. So I definitely see room to grow in that direction. In terms of the second work, there are some alternatives, again, limited with respect to the things that I said, mainly from Microsoft research group that looks at Excel. So this is quite similar. This is our baselines. Basically, completing different rows based on things that you do. They mainly focus on completing the values rather than understanding the function itself, which allows more flexibility in terms of they can use deep learning that generates a monster that we cannot understand as humans, but I want to keep it explainable. So they have some of these implementations. Most of them do not survive the final cut in terms of being as a part of Excel, but this definitely can be something very practical. Yeah.
Thank you.
Any question? Let's take Roee again.